Okay, so now when we get to the domain and range of our toolkit functions, let's go back to our constant function. Specifically, let's look at f of x is equal to 2. So when we look at the domain, that's asking for which values of x am I going to get a value out of my function. And in this case, it doesn't matter what x is, the function is always going to give you 2. So in this case, I'm going to use interval notation instead of set builder notation. They're both good to get used to. Interval is just a bit more compact. So let's look at the domain. I can go all the way down as far to the negative side as I want. I can go infinitely far away, not that that's a particular endpoint, it's just that there's no stopping. I can just keep on going and I'll still get some value out of my function. And it's the same thing in the positive direction. I can get to larger and larger values of x in the positive direction without stopping. I'll still get the same number out of my function, which is 2. So it doesn't matter what x is, I get a value, a defined value for my function, and so I can say my domain is from -infinity to infinity. Now those are not endpoints. It's not like I stop at some number that is infinity. So I would call this an open interval on both ends, so that is my domain right there. Now my range in this case is asking what are the possible values of my function. Now there's only one, which is the number 2. And since the function can take on that number 2, that means that this would be a closed interval, so I'd use the square brackets as opposed to the parentheses or the round brackets. So that's my domain and range for the constant function. Now I notice here when I did my drawing of the identity function, I didn't put on the arrows to say that I could keep on going. So here again for my domain, the function is defined over the entire range of x. No matter what x I give it, it'll spit out an answer because the function is just equal to whatever x is. So I would say that my domain is not limited. I can go from -infinity to infinity, but those are not numbers, those are concepts. And so we use an open interval there to represent, like, I can just keep on going in either direction. My range in this case, since my function is just spitting out whatever the x value is, if I go to x is equal to 10,000, the function is 10,000. If x is equal to 10 million, my function is equal to 10 million. So the limits on my x, of which there are none, are the same limits on my on the values of the function. So my range matches my domain for this identity function. Now for absolute value functions, it's a little bit different. So when I start considering my domain, again, the function f of x is equal to the absolute value of x. That will spit out an answer no matter what x value I give it. So it's defined on the entire, for all of the real numbers, for x going to -infinity and up to +infinity, using those round brackets to say is an open interval. Now my range, though, there is a minimum value of 0 when x is equal to 0. Now it can keep on, as I go to larger x's, it'll keep getting bigger, and more negative x's, it'll keep getting bigger. And so there's no limit in terms of the positive value that the function will take on, but there is a minimum down here of that 0. So I'll say my range goes from 0 to infinity, and it's an open interval on the infinity side, because that's not a number, it's a concept. But that 0 is a closed interval because the function can take on that value of 0. So my range is the closed interval from 0 up to the open interval of infinity. Now, when I look at my quadratic, this is going to mimic, even though it's a different shape, this is going to be very similar to my absolute value function. The domain, the x values where this function is defined really isn't limited. I can go from -infinity to infinity. The range, there is a minimum value here at 0, and the function can take on that value, and then it can get as large as it wants without limit, and so that's fine right there. For the cubic, this ends up matching more like the identity function, the f of x is equal to x, or a general line that's not just a constant. The domain would be from -infinity to infinity, and the range would end up being also minus infinity to infinity with open intervals. When I get to the reciprocal and reciprocal squared functions, this is where things get a little bit tricky. So if I focus in here on my reciprocal function, actually, let me just go back up a bit. If I chose an x was equal to 0, then my function is undefined. So whatever my domain is, I cannot use x is equal to 0. I can go as far as I want down, and I can go as far as I want up, but I cannot include the 0 right there in the middle. So I'm going to say that my domain for this reciprocal function, I can go from minus infinity up to 0, and I can't include either of those. And I can also go from 0 up to positive infinity without including either of those. And it's really the union of those two things. So it's like I'm starting just below 0. That's not technically correct, but yeah. And going down, and then just above 0 and going up. Just excluding exactly the number 0, because the function's not defined for that x value. Now my range, obviously right here I can go down as much as I want and up as much as I want. I just get closer and closer to when x is equal to 0. Now, one thing that's not necessarily obvious is that if I put in this function, if I put in huge values of x, I'm not ever going to get down to identically 0. I can get closer and closer to 0 as my x gets bigger. Remember that f of x is equal to 1 over x. But if I put in x is equal to 1 billion, I get f of x is 1 billionth. And if x is equal to 1 trillion, f of x is 1 trillionth. I just never get to 0 because I can never reach infinity in this particular case. So my range ends up looking very similar. I can go down as far as I want, but I can't get up to 0. And then I can't get down to 0, but I can go up as far as I want. And I'm looking at the union of those two things. Now, for the reciprocal squared, it's again, the domain is going to be very similar. I just cut out that 0 out of the entire x-axis. And for the range, now there's no negative values in this particular case, so here I'm just going to say from 0 up to positive infinity. And the last two toolkit functions, the domain for my square root. So we know that we can have an x value of 0. That's perfectly fine in this case, but nothing that's negative. And I can allow x to get as big as I want, and I'll get some number out of the function. And by the way, you can test this on your calculator too if you're trying to figure out domains and ranges. It's not a bad idea to just guess and check. So my domain includes 0, and it can go as big as it wants. My range also includes 0, and I can get as big as I want. There's no limit to how large I have to get. I just have to choose a very, very large x value. For my cubed root, in this case, there's nothing stopping any value of x. Like I can go down as far as I want to the negative values. I can get all the way to 0, and then I can go to positive values as much as I want. So my domain here is minus infinity to infinity, and that open interval, and the range is going to be similar. Okay, and that's the domains and ranges for all of our toolkit functions.